Okay, so um, this next section is pretty much just devoted to proving one result called the Chinese Remainder Theorem. Um, to Before we can state the result, I need to tell you what it means for two ideals to be relatively prime. So I'm going to let A be just any ring, or commutative. We say two ideals A and B are relatively prime. Prime. What does this mean? This essentially means that their sum is the entire ring. Okay. So if A is the integers, then two numbers, little a and little b, are relatively prime exactly when the sum of their ideals is all of z. Okay. And yeah, so this generalizes your preconceived notion of what it means for two numbers to be relatively prime or coprime. So now, just with this definition, we can state this theorem. So we're going to let A be a ring. With pairwise coprime ideals say A1 through AN. Okay. Then we have an exact sequence. Zero, an ideal A, which I'll define in a minute, embedding into my big ring A, and a family of projections here. I equals 1 to n, A mod. Okay. So let's tell you what these objects are. So A is the intersection of all of these rings, which, as it turns out, the coprimality assumption means that this intersection is also equal to the product of all these ideals. Okay. F is simply the inclusion. And G is the sum of the projections, which takes a little a and gives me a plus a1, a plus a2, and so on. Okay. So I guess maybe another thing I should mention is, what do I mean when I say pairwise coprime here? This means that if you pick any two, if I pick A1 and A4, then those two ideals are coprime. Any pair of ideals in this list are coprime. And the result says essentially that if I quotient out by the product or by the intersection, turns out they're the same in this case. If I take A mod, the product of these ideals, it turns out it splits up as a direct sum. Or a direct product. I guess it's finite, so it doesn't really matter, of the quotient rings. Okay, so quotienting by the product of the ideals is the same thing as taking the product of the quotients in this case. That's what this sequence being exact means. Okay. So let's go ahead and try to prove this theorem. So the first thing we're going to show is this equality here. Okay, one containment is pretty clear. The product of the ideals, well, the product of these ideals is contained in every ideal, so it's certainly contained in the intersection. And by every ideal, I mean every a sub I, not every single ideal in my ring A. Okay, so since ideals have the absorption property, this product is contained in every a sub I, so it's contained in this intersection. Okay. The other direction requires a little bit more work. First, we prove the result when n equals 2. Okay. So when n equals 2, what do we have to show? We need to show that A1 intersect A2 is contained in A1 times A2. Okay. So I'm going to start with A in the intersection. Okay. Since these two elements are coprime, or sorry, since these two ideals are coprime, since A1 plus A2 equals the entire ring A, we can write 1 equals A1 plus A2 for A1 and my ideal A1, and little a2 and my ideal A2. Okay. Then we see that A is equal to A times 1, which is going to be A times A1 plus A times A2, which is in the product ideal A1 times A2. Since A times A1, well, since A is an A2, A times A1 is an A1 times A2. And since A is in A1, A1 times A2 is also in the product. Okay. Since A sits in both A1 and A2, both of these products are in the product. And the sum of two elements of the product is in the product ideal. Okay. So that we get this intersection, A1 intersect A2, is contained in the product. Okay, so this is kind of like a first step in this proof. So next we want to observe, so if we cut the chain off at some point I want to basically like continue this in almost an induction style argument. So next observe that AI is coprime to the product of the first I minus 1 terms as follows. Okay. So for each j less than I, we're going to write b sub j plus a sub j equals 1 with b sub j in a sub I and a sub j in a sub j. Okay, so for each j less than I, I'm going to pick a b sub j in a sub I and an a sub j in a sub I that sum to 1. So this is by the coprimality of a sub j and a sub I that I can do this. Okay, then observe if I take this product over all these b sub j's and a sub j's, j equals 1 to I minus 1. Okay. if you think about expanding out this product, I'm going to get some big term b with all my cross terms, and the product of all these a sub j's. Okay, so this b is the sum of all the terms, any of which containing a b sub j, and we're going to observe where we see that this big B is necessarily an a sub I, because every product here contains a little b sub j, which is an a sub I, and this thing is an ideal. And this product here, j equals 1 to I minus 1 a sub j, is my product a sub I minus 1. So what is the conclusion from expanding out this product? I see that 1 can be written as an element here plus an element here. So thus 1 is in a sub I plus this product a sub I minus 1, and this immediately implies that these two ideals are coprime. Okay, so since 1 is in this sum of ideals and this ideal is an ideal, or the sum of ideals is an ideal, this sum necessarily has to be the whole ring. Okay, so if you apply this result repeatedly, you can do something like this. So if I take this intersection, okay, I know that the intersection of the first two is equal to the product of the first two. Okay, intersect a3 dot an. Okay, and then I apply this result for this ideal and this ideal. Okay, so these two things are coprime by the above work. The a1 times a2 is coprime to a3, so that the intersection is actually equal to the product of these two ideals. So this is a1 times a2 times a3 all intersect an. And then you just keep going down the line and using the associativity of intersections and products, so that eventually you just get the product of all these ideals, a1 up to an. Okay. So applying this result step by step repeatedly, you could also go through and rewrite this as an induction. Somehow this made more sense to me, but gives you the first claim that the intersection of these coprime ideals is actually equal to the product of them. Okay. And from this, the rest of the result won't be too bad. So we show the exactness of the sequence. Exactness. Remember this ideal A, which is the intersection or the product of my coprime ideals, goes into big A, and then it hits into the product here. I equals 1 to n a mod a sub I. Okay, so to check exactness of a sequence, you need to check exactness at every spot. So the first spot I need to worry about exactness is here, and the exactness of this spot is clear because this map is just like the natural embedding, so of course f is injective. So since f is injective, the sequence is exact. The ideal A. Okay. So exactness at big A follows almost immediately from the above computation. So the kernel of G is exactly, so if you think about this for about 2 seconds, you'll see that the kernel of G is the intersection of where all these ideals A sub I, A1 intersect AN, which also happens to be the product, which is exactly this ideal A. Okay. Thus the sequence is exact at capital A. Okay. So what's left to show is surjectivity. Okay. So we need to show surjectivity of G. So I'm going to define an element delta sub I in this product so it's going to be defined as the following conditions: delta sub I sub j, so the jth component, so this is a product, this thing has n different components, or I guess, yeah, n different components. The jth component is either going to be 0 or 1 plus a sub I, and this is going to be if j is not equal to I, it'll be 0, and if j is equal to I, then it'll be 1 plus this thing. So these are essentially a nice set of generators for this ring, or I guess, so note the collection of delta sub I generates this product as an A module so maybe there's some work to check. If you give me a product of elements here, then you can pretty easily figure out what the appropriate coefficients to put on each delta I is. Yeah, so note, if I have a sub I from I equals, I guess really should be, sorry, a sub I plus the ideal from I equals 1 to n, then I'm going to just call this guy A. A is the sum from I equals 1 to n a sub I times delta sub I. Okay, so this is a pretty easy direct computation. So that shows that these delta I generate as an A module. Since G is a map of A modules, okay, it really suffices to show that each delta sub I is in the image of G. So I'm trying to show this map is surjective. I've found a nice generating set as an A module. G is an A module homomorphism. So it suffices to show each element of this generating set is in the image of G. Okay. So really, this problem is fairly symmetric in the sense that if I can show delta 1 is in the image of G, then I can basically slightly adjust the argument to show that each delta sub I is in the image of G. So um, without loss of generality, so by symmetry, I can show delta 1 is in the image of G. Okay. And to do this, we use something we observed earlier. As we saw before, okay, if I take one coprime ideal from above, this will be coprime to the product of the other ideals. Coprime to A2 through AN, which is also the intersection. Okay. This was this induction style argument that we had earlier. So what does that mean? It means I can write 1 equals A1 plus A, where A is in the intersection and A1 is in this ideal A1. Okay, and then G of this guy, G of A1, or sorry, what do I want to say? Yeah, G of A1. Wait, gosh dang it. G of A will map to delta 1. Okay, so let's talk this out. Briefly make sure that this is right. So in the first component, G of A, so notice that A is going to be 1 minus A1. So in the first component, 1 minus A1, this is certainly equivalent to 1 modulo this ideal A1. So I've got a 1 in the first component. And every other component, A is in the ideal A2 through AN. So G of A is certainly going to be 0 in every other component. Okay. So you can imagine, instead of taking A1 here, I could have picked an AI, and then it would have been product or coprime to the product of all the other A sub j's with j not equal to I, and I could have constructed a similar element. So that pretty much completes the proof of the Chinese remainder theorem. There's a similar theorem for modules, so I'll just go ahead and state the theorem. Let A1 through AN be ideals in the ring A. And I'm going to let M be an A module. Okay. Then we get a similar short exact sequence of A modules. What does it look like? 0, math rack A, M, and now it's product. Something is not right here. There should be an AM over M mod A sub I M. So essentially, you can replace A with M for module M. Okay. And the proof is to essentially replicate. So maybe this is a good exercise. If this above proof was confusing, you can go through and carefully kind of reconstruct the proof, but in the case, not when A is a ring, but when A is M a module. Proof replicate the above for module M. Yeah, I think there's some... Yeah, no, yeah. I think this will, yeah, you can... I was worried for a second because M doesn't have a unit in it, but it's not going to end up... You're not going to need to write, like... Yeah, you should be able to pretty much port this proof to the case of modules without too much trouble just by carefully working through it. Okay. Okay. So that pretty much completes this lecture.